Hey there, I hope you did well on your quiz on 1.1 to 1.5. We're going to jump into 1.6 here on solving systems of equations. And so our objectives in this section are to be able to solve systems of linear equations graphically and algebraically. And you see our standard here, ACE point 3, which is solving systems of equations and inequalities with some real world situations, and we will get to some of that in the assignment for 1.6. I first want to talk about what methods there are to solve systems. And so you see there's a list of 6 here. The 3 that we talk most about are numbers 2 through 4, graphing, substitution, elimination. That's what we worked on in Algebra 1 for the most part. You might have talked about how to solve with the table a little bit. I'm going to show you one example of that today. But one method that I would highly recommend, especially for those of you getting ready to take ACT and SAT, is matrices. This method is very quick with your calculator, and so my plan is to do a separate video on matrices later on so you can see how that is done. Lastly, there's Cramer's rule. Cramer's rule is one that you will learn in upper calculus. Very useful method for large systems and for systems with multiple variables, talking 4, 5, 6, 10 variables. Okay. So let's look at example 1, solving by using a table. So we're going to solve this system here, x plus y is equal to 3, and negative 2x plus y is equal to negative 6. And so first off, we need to choose a point to just plug in and start solving for. So I'm going to start with 0. And we're going to see if these values get closer to each other or further away from each other, and then we'll know where we need to kind of hone this in. And so putting in 0 for x means that y would be equal to 3. And so this I'm calling my y1 equation, and this is my y2 equation. And if I put in 0 here, I get negative 6. So the question becomes, if I go to 1, is this going to get closer or further away? Well, plugging in 1, so I would subtract the 1 to get 2, so that gives me 2 for this y. Put the 1 in here, I get negative 2. Add that across, we get negative 4. And we look at how far apart these are. These were 9 apart when we talk about the absolute value of it. And these were 6 apart. So are we getting closer or further away? We're getting closer. So let's take this a couple steps. Well, it looks like it goes down by 3 here. So maybe if I go 2 more steps, I'm going to skip 2 and go to 3 and see what happens. Plugging in 3 for x here. So 3 subtracted over, so I get 0. Plug in the 3 here, I get negative 2 times the 3 is negative 6. Add the 6 also gives me 0. And so the y's come out the same. It's when we get the order pairs to be the same, that is where these two lines will finish up. And so the solution to this is 3, 0, because here's my x, and this is the same y for both. Now, if you're given a table across, instead of just giving the equations, you can see where this happens by, again, looking at the y values. And let's say you see it where the values change, but you don't actually see the same point. You can see that it will fall between 2 integer values that you're given. So scrolling on down to example 2 here, solving by graphing. So we just need to remember how to graph in our 2 methods. I'm going to skip example A actually and go straight to example B because I've got one in standard form and I've got one in slope intercept. And so remember, to graph out of standard form, we could do one of 2 things. We could either plug it in and get our x and y intercepts. And the y-intercept here is going to be a fraction, so maybe we don't want to do that with this. But just for the sake of it. So remember that I plug in 0 for this y, so x would be equal to 7, so that's going to give me that. And if I plug in 0 for the y, divide by 3, I get that the y-intercept would be 7/3, so a little above 2. Now, if we wanted to go into slope-intercept form, remember, subtract the x, divide by 3, and so we're going to get that y is equal to negative 1/3 x plus 7/3. And so there's that 7/3 appearing anyways. And so going from here, we go up 1 and left 3, up 1, left 3. And so we start to see that line evolving through there. Our second line is y is equal to 2x plus 3, so again in slope-intercept form. So my y-intercept is 3, my slope is 2, so I'm going to go up 2 and right 1, down 2, left 1, and we see that my crossing point's in here. Do I get a nice perfect point there to take? Not really. And that's the issue with graphing, is unless it comes out to a really nice point, we're going to estimate. And so here the estimate would be probably about like maybe negative a third for x, and then 2.5 for y. Again, I'm guessing here without using technology and not trying to solve it using other methods. But that's about where it's at. Maybe it's got to be more than 7/3 because that was the y-intercept of the first line. So that's why I'm going with a half, just to kind of boost up towards the middle of that box. So that's why I don't recommend graphing in most circumstances. I recommend that you use an algebraic method to solve most systems. So let's talk about how our systems can be defined. We have 3 systems. And so I'm going to draw 3 coordinate planes over here. There's 1, there's 2, and there's 3. And so I want to talk about these 3 cases for a second. And so our first case is if I have 2 lines on the coordinate plane that intersect like such. And so it has a point of intersection. That's the one we're used to. We're used to getting some type of order pair x, y out of that. And we'll talk about these definitions in a second. So one solution here, right? One solution. Our next system that we're kind of used to, and we see it every once in a while, but not often, is when the 2 lines never touch because they are what? Parallel. Well, this gives us no solution, right? Because remember, to have a solution, the 2 lines must meet somehow. Our third type is one that we see very seldomly, but we do need to talk about it. So there's my first line, and watch what happens with the second line. Right on top of it. They're the same line. And so in this case, where's the solutions? Well, this has infinitely many solutions. Because all the solutions are every point along that line. So let's talk about a couple terms that we have. So a system is consistent. A system is consistent if it has at least one solution. So that would be graph A and graph C, right? Because there is at least one solution here. There's infinitely many. We can't count them all because it's every point along that line. And it is the opposite of that, so inconsistent if it has no solution. And so that's graph B, right? Because they don't touch. Now, if a system's consistent, meaning it has at least one solution, it falls into one of 2 cases. It can have one solution, and so we are going to call that independent because our 2 lines do not depend on one another to find the solution. And what I mean by that is that I can move one line, I get a new solution, right? Whereas if I'm in case C, where the 2 lines are the same, those 2 lines are dependent on each other because if one line moves in some way, I don't have all those solutions anymore. And so we're going to look at a couple of examples here to classify systems. And so these are by graphing. And so these are, again, in standard form. Now we're going to look at this first one here. This one's not going to be good to graph in standard form because the C is equal to 0. And so solving this out, we're going to get that 15x is equal to 6y. Divide both sides by the 6, so we get that y, and I know I'm flipping the equation here a little bit, is 5 halves x. And so going through the origin, up 5, right 2 ends me up there, and I can continue it up here. And again, with these graphs, it's important to be as precise as possible, especially when graphing systems, so that you can see where the intersection happens. My second equation I can do in standard form, so plug in 0 here, divide by the 5, so that'll give me 2, so I'll get a x-intercept of 2. And for the y, I'm going to divide that, let's not use red, divide that by the -2, divide that by -2, and so I get a y-intercept of negative 5. And so when we graph this line, if we look, I'm going down 5 right 2, down 5 right 2, up 5 right 2. This looks like it's going to be what? Parallel. And so go back to our systems, right? To have at least one solution means it's consistent. This has no solution, so it must be inconsistent. And again, it's because it's a parallel system. Okay? And so we can look at other examples of that and understand what type of systems are involved. I'll give you a hint on example B here. These are your three methods, so choice D isn't even an option. They can't be none of the above because those are your only three options for systems. And so when we look at these two lines, again, we're going to look at how to graph them. And so x plus y is equal to 3, so I've got an x-intercept of 3, and I've got a y-intercept of 3. I'm going to move, so let's graph that line real quick. It's going to come through there, and come through, not there, there. Let me get my lines in the right spot and not be messing this up. Putting points in the wrong spots. So there's my first line. Second line, again, we could do 0 for x, 0 for y and solve. So 0 for x means I got to subtract a 6, divide by negative 2. So y would give me positive 3. Let's see what happens with this. There's 1 point of similarity. Will it be the same line or will these intersect? Well, when we do the y-intercept, 0 there, 0 for x, solving for the y, we've done this backwards. But, so 0 for y, solving for x gave us 3. 0 for x, that's the steps we just did, would have given us 3 here. And so we see that these are the same line. And so if they're the same line, remember they're consistent because you have at least one solution. But these two lines are dependent because they are the same line, okay? So let's talk about substitution real quick. And again, this is mostly review. You should have learned this in 8th grade and Algebra 1. So step 1, solve one of the equations for one of the variables. Step 2, substitute the remaining expression into the other equation in place of the variable and solve for that variable. Substitute to solve for the other variable is step 3. And then write the answer as an ordered pair is step 4. And so we got a word problem here, and so that means we're going to have to build our equations. So let's see how we build them using these steps. So Lugol Furniture Store builds 2 types of wooden outdoor chairs. A rocking chair sells for $245 and an Adirondack chair with a footstool for $340. The books show, so what they took in, that last month the business earned $14,230 for the 48 outdoor chairs they sold. So how many rocking chairs were sold? And so we're going to set up our 2 equations. And when we're given a model like this, what we're looking at is 2 things. The first equation here is going to be based on cost and how much these chairs are worth. The second is just going to be on the number of items. So in this case, the number of chairs that we sold. This is the easier equation because let's use some variables here. Let's use R for rocking chair and A for Adirondack. And so the number of rocking chairs plus the number of Adirondacks is equal to the total number of chairs I sold, 48. The cost, remember, would be based on the number of chairs that I sold for how much. And so we get 245 times the number of rocking chairs that I sold. So if I sold 1 rocking chair, I make $245. If I sold 10, I make $24.50. Plus the cost of the Adirondack, so 340 times A. That's equal to the total amount that we earned of $14,230. So now we've got our 2 equations built. And again, make sure you get them built right first. And so step 1 says to solve one of the equations for one of the variables. And so I'm going to solve the second equation for A. So that means I'm going to subtract the R from both sides. And so I get A is equal to 48 minus R. Step 2 says I take all of this and plug it into that variable in the other equation. And so I'm going to get 245R plus 340 times, now substituting in 48 minus R, is equal to 14,230. Now, this is where you might want to have a calculator out for some of these because these numbers will get large and you're going to have to deal with them. So just deal with that as you go along. So we have the 245R plus 340 times 48 is going to be 16,320 minus 340R. Don't forget to distribute. And so now we can combine like terms. These are on the same side of the equation. So the 245R minus the 340R. That's going to give us, let me change colors here, negative 95R plus the 16,320 is equal to 14,230. Uh-oh, we're running out of room. We're going to subtract the 16,320 from both sides. And so 14,230 minus 16,320 gives us a whopping negative 2,090. And so we divide both sides by that 95, that negative 95. And we get that R is equal to 22. So R stood for the rocking chairs, right? And so in this case, we found what we're looking for, that they sold 22 rocking chairs. I didn't have to go any further. Now, had they asked how many rocking chairs and how many Adirondacks, then of course we could plug, that's what the last steps are, substitute for the other variable, and then if we're just doing two equations, write as an ordered pair. But they asked for the rocking chairs, so I don't have to go any further. And just a little hint here, that's what the SAT or ACT will do a lot of times, is they won't ask you for the whole ordered pair in these word problems, they'll ask you for one piece. And so you got to pay attention to which piece they're asking for, and, you know, save yourself some time and steps because you don't have to go as far if you solve it correctly and quickly. Because again, time is of the essence on the SAT and ACT. All right, so that is substitution. I'm going to skip example B for the sake of time. Again, if you want to look at it, be my guest, and if you want me to check your work, I will. But let's look at elimination. Elimination says this. So step one is to multiply one or both equations by a number so the equations have a variable with opposite coefficients. And so what we're talking about there is that we want the variables to be the same number but have different signs. Step two, add the equations eliminating that variable and then solve for the remaining variable. Step three, substitute in like we did before. And then step four, write our answer as an ordered pair as necessary. So I'm actually going to use example B because that one's a little bit more interesting of a problem. Actually, yeah, we will use example B. And so with elimination here, we want the variables to be the same, right? So I've got x plus 3y is equal to 5, x plus 5y equals negative 3. And so we look at the system, and these are both x's, but they're both positive. So to get them to be negative, I can distribute a negative 1 along this entire line. And so what we're going to get is x plus 3y equals 5, and then negative x minus 5y equals a positive 3. And so our step said to then add these equations together. Well, x plus negative x cancels. 3 plus negative 5 is a negative 2y, and 5 plus 3 is 8, meaning that my y is equal to negative 4. Now, the other part of the step is take this and plug it back into an original. First or second, it does not matter which one you want to do. All that matters is that you plug it into one of them. And so just based on signs, I'm going to plug it into the first. So x plus 3 times the negative 2 is equal to 5. X plus, it's actually going to turn to minus because it's positive times negative. So x minus 6 is equal to 5. So add the 6, and we get that x is equal to 11. And so my final order pair is 11, negative 4. Remember, x comes first, y comes second. Don't get those backwards. All right. last thing we need to talk about, so we've talked about our three different types of systems, but we need to see what happens when they solve out. So let's look at this first example. We've got a couple different ways we can attack it. But if we look, we can, you could even divide this down and get it down so that x is 1 and x is 1, because these will all divide by 5, these will divide by 2. Or you can multiply up, and so we've multiplying so that the x's will cancel to 10. And so you can multiply this top line by 5, multiply this bottom line by 2. And so we get 10x plus 20y is equal to 60. And our second line is negative 10x minus 20y is equal to negative 60. And so when we add those two together, what we're going to get, 10 minus 10 cancels at 0. 20 plus negative 20 is 0. 60 plus negative 60 is 0. So we get 0 equals 0. Everything cancels. And so in this case, what this means is that everything's a solution, right? Now, that doesn't mean the entire graph is a solution, the entire coordinate plane. But what it means is that this line, 2x plus 4y is equal to 12. Or the other one, we could use the negative 5x minus 10y is equal to negative 30. This is the solution to the system, because what's going to happen is that these two lines are the same line. And so this graph would look something about like that, because it would have a y-intercept of 3 and an x-intercept of 6. So last example here that we're going to look at is x plus 7y is equal to 8, 2x plus 14y is equal to 10. And so I'm going to multiply this top line by 2, actually negative 2, so I can get the signs to be opposites. And so I get negative 2x minus 14y is equal to negative 16. And 2x plus 14y is equal to 10. When I add these together, that cancels. And that cancels because negative 2 and positive 2 is 0, negative 14 and positive 14 is 0. And so that gives me 0 is equal to negative 6. That doesn't make any sense, because 0 is supposed to equal to 0 like we saw in the last equation. And so what this means is that we have, as we've learned before, no solution. When we get a false statement where a number equals some other number, it can't be anything. And so no solution here, which means that these two lines are parallel in some way. They'd actually be having negative slopes. But they're parallel. That's the point. All right. So that is 1.6 in a nutshell, solving systems of equations. If you got questions, you know what you got to do. Ask. And your assignment is in Google Classroom. You all have a good one. Except I almost forgot the word of the day. And so the word of the day today is consistent.